a new section today, which is on the energy-based Lagrangian method. So this is another approach to doing mechanics that has some advantages. Maybe it even has some disadvantages, but let's think about the advantages. I'm going to go through a quick example, but I wanted to give you an idea of what some of the advantages are. So let's pull up something here. Where is it? So this is the Cart pendulum system that we've looked at before. And usually the way that we've treated this, we've got the cart is moving along some kind of horizontal line. There's this, so we have a constraint. So when you've got constraints present, and we'll kind of introduce what that is, the idea of a constraint becomes very important in Lagrangian mechanics. But if you have like a mass or rigid body that's moving along, it's constrained to be on a track, then that will lead to reaction forces. Or even in this case, if we've got the pendulum bob connected to the middle of this mass up here, there's a constraint there, rigidity constraint, saying that the distance between Q and P is always constant. So when you have constraints present, that leads to needing to calculate reaction forces. Related to those constraints. And those end up being cumbersome, they take up time. What if all you wanted to know is just the dynamics of, say, how this thing moves? So you pick some variables like x, the horizontal distance of the cart, and theta, the angle of the pendulum. Well, Lagrangian mechanics allows you to skip the calculation of reaction forces. So you might want them for some reason. Maybe you want to know, is the reaction force so great that the material will break? But the Lagrangian mechanics allows you to ignore reaction forces, basically skip that step, and just get at the dynamics of the free variables that describe the system. So in this case, you'd get something like x double dot equals something and theta double dot equals something without having to worry about calculating pesky reaction forces. So this is more efficient. It's a more efficient process to get the equations of motion. And it does this via energy. Let me show an even simpler one, and then I'll even do a mysterious calculation for it. The pendulum. So in this case, that upper block up there doesn't move. It is inertially fixed, and we're just going to get the equations of motion. So here's the simple planar pendulum. So I'm not going to I'm going to do a calculation, but you won't know why anything is happening. But we're going to calculate the kinetic and potential energies, and later we'll say why. So for the kinetic energy, let's say that this pendulum bob has mass m. So the kinetic energy, we know for particles, is 1/2 m, the magnitude of their velocity squared. Now, if this is a pendulum, it's sort of already set up for using polar coordinates, but we know there's not going to be any motion along the pendulum, along the rod direction. The only motion could be along the theta direction. So according to polar coordinates, this is 1/2 m, and then this is L theta dot squared. We've got 1/2 m L squared theta dot squared. What about the potential energy? Here, the potential energy is due to gravity. And we've all learned probably it's mgh, where you need to pick the height. Here, it's convenient to use the height of the pivot point of the pendulum. So if we use that, then it's mg, and this is negative L cosine theta. Okay, so this is negative mgl cosine theta. So from the kinetic and the potential energy, we now construct something we call the Lagrangian function, which is written as L, and it's going to be the kinetic minus the potential energy. And in fact, it'll be a function of the variable that describes our system and its time rate of change. So theta and theta dot. And if we just write this out, so what is this? 1/2 m L squared theta dot squared. And then this is minus a minus, so this becomes plus mgl cosine theta. So we've got our Lagrangian function. And now the Lagrangian procedure would be that we take certain partial derivatives of this Lagrangian function L and plug into what's called the Lagrangian equation of motion. So the Lagrangian equation of motion is the total derivative partial L partial theta dot minus partial L partial theta equals 0. So let's just plug in. So total derivative of partial L partial theta dot. So the only place where theta dot is here. So this means m L squared theta dot. We're going to take the total derivative of that. And then minus, what's partial L partial theta? This is minus mg L sine theta equals 0. Okay, if we take this total derivative, the only thing that depends on time is the variable theta and also theta dot. So this becomes m L squared theta double dot plus mg L sine theta equals 0. Cancel things out, and what do we get? We get theta double dot equals negative g over L sine theta. And so this is the same as we got in an earlier lecture. And that's the only point here. That, okay, there's something, we do some kind of mysterious formula. We do kinetic minus potential energy, not kinetic plus. And somehow things work out. And all we did was carefully write kinetic and potential energy and then carefully take some derivatives. We didn't really, after this step up here of getting the kinetic energy, we didn't even have to think of vectors really. So that's part of the appeal. This is why it's called analytical dynamics. When people say analytical dynamics, they're often thinking of Lagrangian dynamics. So writing things just in terms of scalar variables that describe the system. In this case, it's that angle theta. That's it. So that's called a configuration variable. So this is just supposed to be a kind of tantalizing preview of, okay, how does this work? What will we be doing? we'll get to why it's, kinetic minus potential. There's other advantages to the Lagrangian method that you'll probably see along the way. And one of those is that you can use any coordinates you want to describe a system. You're not stuck with like Cartesian coordinates or polar coordinates. You can use any coordinates that describe the configuration of your system, which is important, especially when you have more complicated things. So let's go through this more carefully and start some steps towards this Lagrangian approach. So we're going to have to take some baby steps, or let's say initial steps. Or the Lagrangian approach. Now, the book we've been using does have a chapter on this. So if you want, you could see chapter 13 of Kasdan and Paley. There's another book, Greenwood's book on advanced dynamics, and chapter 2 of that is quite good. It's also worth getting the whole book, but because this book is more focused on analytical dynamics, whereas it's just that chapter 13 of Kasdan and Paley that talks about this. Okay, so what are we going to be looking at first? We need to talk about things called generalized coordinates. And this will lead to the idea of degrees of freedom. Which is also inextricably linked with the idea of constraints. And there's two major varieties. They go by the names holonomic, which are constraints on the configuration variables, and non-holonomic, which means everything else. But typically it means constraints related to time rates of change of configuration variables. The simplest one being like things related to rolling without slipping. Okay. So right now, let's talk about these generalized coordinates. And so all of this is in, if you want some initial place to look, section 13.1 to 13.2, Kasdan and Paley. Let's look at first the one particle case. So we've got an origin, and we've got some unit vectors. And now I'm using A. So let's call this the A frame. And there's a particle P. And we want to know what's the vector from O to P. So what is the location of P with respect to O? And we'll say it's got, three components. So there's A1, there's A2, there's A3. This is without the hat. So we have the unit vectors, the little hats on them. But this vector R P with respect to O, we could write it as A1, a scalar, describing how far we are in the A1 hat direction, plus A2 hat, plus A3 hat. And maybe it's more convenient for you to write this as a column vector that describes the location of that point P. Now suppose, and this would be like a typical Cartesian approach to writing the location of particle B. But suppose we chose some other set of 3 scalar coordinates. Of 3 scalar coordinates. And I'll call these Q1, Q2, Q3. And so it's just some other set. And this is where we get this idea of it's kind of generalized. These are generalized coordinates. And what do we mean? We mean that, I mean, you could think of it this way. A1 can be written in terms of Q1, Q2, and Q3. Same for A2. So all of these original scalar coordinates, the A's, can be written in terms of the other scalar coordinates. Okay, so something like that. And so now we can write R and right, we're trying to track things as they change in time. So R PO as a function of time in terms of Q1, Q2, and Q3, which are our new variables, meaning they vary with time. So because we could do that, we have some freedom in how we write the velocity. So let's say, you know, here's the velocity of that point P, meaning velocity with respect to this A frame of P. Oh, what is the velocity? What is that vector? And we would use the chain rule. So we would first look at how the so take sum from 1 to 3. It's partial A1, right? Partial QI times dQI dt. All of that in the A1 hat direction. And then the same for the other 2 directions. So we're just using the chain rule, and that these A1, A2, and A3 are functions of the Q's. We want to use the Q's. So now partial A2, partial QI, dQI dt in the A2 direction, plus sum from 1 to 3, partial A3, partial QI, dQI dt. And that's in the A3 direction. So we can write the velocity, right? These partial A, partial Q's. So partial, think of it this way, partial AJ, partial QI will be a function of the Q's. And these things that are dQI, dt, we could just write that as QI dot. So that means that the velocity that we care about is a function generally of, you know, Q1, Q2, Q3, and also Q1 dot, Q2 dot, and Q3 dot. All right. And similarly for the acceleration, if we were to write what's the acceleration of this point, I don't know. So let's write it that way. It's the acceleration of this point P. Acceleration of the point P with respect to O, that vector will pick up another derivative. So you would just use the chain rule applied to this thing above, this expression for V. So this acceleration can be written in terms of Q1, Q2, Q3, Q1 dot, Q2 dot, Q3 dot, and then Q1 double dot, Q2 double dot. So just two time derivatives of this variable. Okay. We're not going to go through what that calculation is. Just know that it can be written in terms of these generalized coordinates and their time rates of change. So you could do that. This was for the one particle case, right? The one particle case. Of course, we could do this if we had the multi-particle case. So if you had n particles. So you can also do this for the multi-particle case. Or a multi-particle system. So if we had some frame, and we've got multiple particles, let's call this particle 1. So here's location of particle 1 with respect to the origin, and particle 2 with respect to the origin, and so on, particle 3 with respect to the origin. So if we have n particle positions, and let's just write it as Ri, location of particle I with respect to O could be written in terms of a set of Qs. We would need more than 3. I don't know how many. Let's just say little n. So that means little n generalized coordinates. Wait, so isn't little n equal to 3 times big N? Well, maybe. Or maybe the same coordinate can be used to describe more than one of these particle positions. But right now, think of, we've got capital N particles that could be described by little n generalized coordinates. Then we could get their velocities, we could get their accelerations, and at the end of our calculation, we would say that, applying Newton's laws, we'll get some equations of motion. In the form of second order ODEs for the Qs. So like Q1 double dot equals something. I'll just put some dots all the way down to Qn double dot equals something. So we've got second order derivatives in time for these Qs. The right-hand side here is a function of the Qs and their time rates of change generally. So this is n second order ODEs for the Qs, which we can solve given initial conditions in principle. Maybe they're solved numerically, but they can be solved given initial conditions to give us what do we want? We want to know how do the Qs change in time, and then from that we could reconstruct how does particle 1 move in time, all the way to how does the vector that describes where's particle n. So our ultimate goal, you could say, is to know where these particle locations are, but all of the background work is done in terms of generalized coordinates. And we introduce these generalized coordinates because they lead to more flexibility in how we describe our sets of particles and how they evolve. You could also view the the Q's and the Q dots as this is a abstract space. It's 2n dimensional phase space, or sometimes people call it state space. There's no big difference, but it's just sort of it's hard to draw something that's 2n dimensional. But let's just say, Q1, Q2, Q1 dot, Q2 dot. If you start with some initial condition, like this green dot here, and then you simulate, so solve for what the ODEs do, then you'll have some kind of path that your system is traveling in this state space. So this is the evolution of the system in state space or phase space. I'll use the terms state space and phase space interchangeably because there's no difference. And if you know how the system evolves in this state space, then you can reconstruct how is the system actually moving in physical space. And how do we get these second order ODEs? We're going to do it through this thing that we call the Lagrangian function. So the Lagrangian will be a function of the Q's and the Q dots. And it's just going to be the total kinetic energy of your system minus the total potential energy of your system. So any forces that come from a potential energy, which we've also come to call conservative forces, will be described by this scalar function U. Anything that's not, so anything that's a non-conservative force will end up being we'll be able to write it as a generalized non-conservative force, but we'll get to that. So, some of this may be new. It's okay. Okay. Now we need to talk about constraints and degrees of freedom, because these are tied to the choice of generalized coordinates or what we even mean by generalized coordinates. So constraints and degrees of freedom. If we have a system of capital N particles in 3 dimensions, then we need to say something else where there are K constraints present. We'll say what a constraint is. And then the number of degrees of freedom is related to these. And the book uses capital M. So the number of degrees of freedom is, let's say so if you have n particles in 3 spatial dimensions, you might think, okay, then it's 3 times n. It's like you need 3 Cartesian coordinates for each particle. So it's 3 times n. But then if you have these constraints, then you subtract off the number of constraints. So K is the number of constraints. And this will mean something to you later, but this is just for holonomic constraints. So a holonomic constraint is it's a scalar equation that relates generalized coordinates. So we'll write things this way. This is f, and this is sub little k. We'll write it in terms of particle location vectors. So if we've got some constraint, it's a function of these vectors and possibly time. And this is the common way to write it. So you've got some scalar expression. This is a scalar. And little k goes from 1 to big K, capital K. So this is a relationship that relates the vectors, but you could also think of it as, when you write it in terms of the generalized coordinates, then we write it as maybe phi. So phi sub k is written in terms of the q's and possibly time. So you could write it at the level of constraining how these vectors are related, or in terms of how the generalized coordinates are related. Let me give you an example. Okay, so here's an example. We've got a particle. We'll just have a single particle constrained to a curve y equals h of x in the xy plane. And so here we're just using as our generalized coordinates the usual Cartesian coordinates. So we'll say Q1 is X, Q2 is Y, Q3 is Z. So we got 3 generalized coordinates. We're talking about one particle. So capital N is 1, little n is 3. And let's kind of sketch what's going on here. If we had the X going that way, Y going that way, then for a right-handed coordinate system, Z would be going out this way. But we're constraining the motion to be in the XY plane. So how do we write that as a constraint? Well, we would write Z equals 0. So if you want, we would say, okay, F1 equals Z. F1 of the, it's a function of the location of this particle. There's only one particle. So here's our origin O. Here is particle P. No, I guess we're calling it particle 1. So that vector has to be in the XY plane. We're also saying there's some curve. And this is writing it as it's a function. Y is a function of X. We don't know what it is, but we're just calling it H. So that's another constraint. And if we want to put it in this form of something equals 0, we would say y minus h of x equals 0. So we have 2 constraints. Here's constraint 1, here's constraint 2. Like we could write this f2 as a function of this particle vector is y minus h of x. And we're requiring that, right, F1 equals 0 and F2 equals 0, which means both of these constraints are satisfied. So if you think of how many constraints do we have? We have capital K equals 2. And the number of degrees of freedom for this system right, it should be 3 times n, and n is 1. So it should be 3 if there weren't any constraints. The particle could move through freely in 3D. Minus k, right? Looking up here, it's 3n minus k. So we've got 3 minus 2 is 1. There's only 1 degree of freedom. And how do we understand that 1 degree of freedom? Well, it's like this mass can kind of slide along that blue line, and that's it, the blue curve. So mass 1 is only free to slide along the blue curve. A curve is a one-dimensional thing, so you could write, you could hopefully see, it's kind of like a bead on a wire in the XY plane. So understandably, because you can only move along the wire and a wire is one-dimensional, this is a 1 degree of freedom system. And what would you use as that degree of freedom? Well, this is where things get interesting for the Lagrangian approach. You might say, well, I could use X, you know, given how the curve was drawn here, you could use X as that degree of freedom. But you would have, you could have other choices. Maybe you want to use, you pick some kind of tick mark here and call that your origin. And then you're tracking the arc length of where this is. I don't know why horizontal lines keep showing up. So this is the arc length along the curve from some reference point. So you could use X as a generalized coordinate, or the arc length S, or something else that's more convenient. And that's sort of the power of generalized coordinates. Any of these could be used to write the equations of motion, and some might be better than others. Now there's something interesting when you've got a certain number of degrees of freedom and you have a holonomic system. So that means you can write constraints in terms of the generalized coordinates themselves, not their time rates of change, just the generalized coordinates. So in this case, right, this constraint is z equals 0. This is y minus h of x equals 0. It's always theoretically possible to find the minimum set of generalized coordinates. I should say for a holonomic system, meaning for a system with holonomic constraints. So I know there's some new terminology here, not a holonomic, holonomic. For a holonomic system, this just means a system with only holonomic constraints. It is always theoretically possible maybe let's highlight that. It's always theoretically possible to find the minimum set of generalized coordinates. And the book uses the terminology NC equals M generalized coordinates. So meaning we could pick a set of generalized coordinates that is equal to the number of degrees of freedom, meaning we don't have any extraneous generalized coordinates. We can pick generalized coordinates. Pick as many generalized coordinates as degrees of freedom. And I'm probably going to start writing just DOF, and I'm not going to say DOF. I'm going to say DOF, degrees of freedom. And there's no extraneous degrees of freedom. Well, they're not degrees of freedom. There's no extraneous generalized coordinates. So for example, for this case up here, X would be that's just one generalized coordinate that also equals the 1 degree of freedom. There's also the arc length. That would be legitimate. It's always theoretically possible, but sometimes hard to do in practice, let's say. I want to give us some practice writing, some looking at systems and trying to figure out how many degrees of freedom they are. So we're going to look at some examples. Suppose we had, let's say, an n equals 2 particle system in 3D with no constraints. With no constraints. And so we're asking the question, how many degrees of freedom? And I'm looking for responses. So, okay. So you can turn off your mic, turn on your mics and answer. How many degrees of freedom is this? Two particles in 3D.
Isn't it 6 with no constraints?
Yep, 6. So yeah, you could think of it as if we had two particles. I mean, the simplest thing would be, so let's call this particle 1. We got X, Y, and Z for particle 1, X, Y, and Z for particle 2. That works. Or we could do spherical coordinates for each one. That's part of the freedom you get. What if we had, this was in 3D, about n equals 2 particles in 2D. So the two particles are free to move in the same plane. How many degrees of freedom is that system?
Four.
4. Yeah. Yeah. So you could think of it as starting with the 3D system. If we now impose these constraints, so F1 equals, say, Z1 is 0. That's the first constraint. F2 as a function is Z2 equals 0. So now we've got capital K equals 2. So the number of degrees of freedom is 2 times 3, so 6 minus K. So 6 minus 2, 4. But you could also probably just see it as, all right, if I'm in the plane, what do I have? X1, Y1, and X2, Y2. For each one, I have 2 degrees of freedom. All right, so what if I have n equals 2 particles in 2D, connected by a rigid rod. What's the number of degrees of freedom? So if you know, we've got the same situation as above, but now we've connected them by a rigid rod. How many degrees of freedom is this system?
3.
Yes. Good. Okay, so it's like we had the same thing above, but now we've got another constraint on the location of these two particles, and that constraint is, you could think of it this way, it's the distance, so x2 minus x1 squared plus y2 minus y1 squared. That's the distance between the two. It has to be equal to some constant. Let's call that length L. And that equals 0. So x1, y1, x2, y2. So for this situation, right, we've got now a third constraint. So the number of degrees of freedom is 6 minus 3, so it's 3. And like I said, it's always possible theoretically to find a set of generalized coordinates that equals the number of degrees of freedom for these types of cases. So in this case, if we did x1, y1, x2, y2, well, these aren't all free to vary. There's this constraint up here. So this does not work as a minimal set of generalized coordinates. What we could do is actually use this this angle theta. So a minimal set of generalized coordinates. This isn't the only one. This is just one possibility. We could say x1, y1. So we specify the location of one of the particles, and then we give the angle of the rod. And that would be enough to completely specify the configuration of this system. Think of this as two masses connected by a rigid rod. All you need to know is the location of one of the particles, say this, the one down here. And if you know the angle, then you know where this other particle is. So yay, you can find a minimal set for that case. Of course, that's not the only one. Dynamically, it might be more important to know where the center of mass is. So if I have this rigid rod and there's some center of mass somewhere, well, I could give the coordinates of the center of mass x, g, y, g, and maybe I don't want to do an angle with respect to the x-axis. Maybe I want to do some, this angle or something. So then this would be another set. Another minimal set. Kind of the mental check for, is this a minimal set, would be, can you arbitrarily specify the variables? In this case, yes, we can. We couldn't arbitrarily specify x1, y1, x2, and y2 because of this constraint, but we could specify the location of a point, like the center of mass, and an angle, and then those are free. Okay. So you could dream up all kinds of situations here. Here's another one. What about a rigid body in 2D? So here's a, some kind of rigid body. How many degrees of freedom? Let's say it's free to move in 2D.
2.
How many? What was that?
2.
2. Try again.
3. 2 translational, 1 rotational.
That's right. Yeah. So this, right, you could specify a point either at the end or kind of like above. You could do the center of mass, xg, yg, and then maybe the angle that this thing makes. So it's 3 degrees of freedom. And yeah, you could decompose it as there's 2 translational ones plus 1 rotational. So this could be a car, right, flipping through the air in the longitudinal plane. You could track where the center of mass is, which requires 2 coordinates, and then the angle, which just requires 1. So here, this is a minimal set. It's not the only one. xg, yg, and some angle. We could actually pick any point on the body and some angle, and that would be good. What about 2 rigid bodies in the plane? What's the number of degrees of freedom? There's no tricks. It's just 2 rigid bodies. They're not connected or anything. How many degrees of freedom?
6.
6, yeah. So maybe this one, I'll draw this, and then I'll draw some kind of weird arbitrary shape. So yeah, 6 degrees of freedom. Now, but what if I connect these 2 rigid bodies? So I've got 2 rigid bodies. It depends on how the attachment is made. If I fuse them together, then they're just 1 rigid body. So let's say I don't fuse them. They're attached by a pin joint. You could also call this it's a revolute joint, a hinge. So if I've got here's like rigid body 1, and then connection to, I don't know how to rotate that rigid body up there, but something like that. Okay, how many degrees of freedom is this?
Would that be 5? Maybe?
No.
Is it going to be 3?
No.
4?
4. Yeah. So I mean, it's like this situation up here, right? I've got one of the rigid bodies. You specify the point and an angle, but now I also have. Let me sort of draw an axis along this, and then. So I just need to specify like this angle. So I've got this rigid body. Let's say x. G, Y, G, I've got this angle, theta, and then this other angle. So XG, YG, theta, and then phi. That seems to completely describe it. So yeah, in my office, I had some kind of hinged thing. You sometimes have to either build these or maybe make a CAD thing to kind of see it. So this is 4. 4. It's hard to, I guess you're like, well, you know, what would I have written as the 2 scalar constraints? Well, since we're talking about rigid bodies, you know, we're kind of going into some other direction here. But this is 4 degrees of freedom, and we can write the minimal set. This is one choice of minimal set. There's a situation called the double planar pendulum. which maybe you've seen. So what we did up above was the, so this is the double planar pendulum of rigid bodies. Essentially, this is just taking this system here, but I put a pin joint. So, and usually, you hang this from something. So if I take that rigid body and I've got it now attached by a pivot here, and then there's this other connection. What's the number of degrees of freedom for this?
2.
Yeah. So it seems like when we sort of pin things, we lose 2 degrees of freedom. So yeah, this just becomes, this is 2 degrees of freedom. And we might describe it by 2 angles. So let's say, this angle, theta 1, and you could use this angle, theta 2. So that would be a minimal set. And, you could have all kinds of fun stuff like that. This is where the double planar pendulum of rigid bodies, you could do a double planar pendulum of particles. And it would be the same thing. So if I've got a mass and then some other mass, and those are all the joints are Revolute joints, then I could do the same kind of thing where I do theta 1 and then theta 2. I could also, so this is where generalized coordinates are important. You could write the sort of relative angle, and maybe we would call this V2. That's another legitimate choice. So this is 2 degrees of freedom, but we could use this relative angle, V2. So you could have theta 1 and then V2, and that would be completely fine. All right, what about, this is where it gets all kinds of fun. What about a single rigid body in 3D? And it's free to move in 3D. It's free to move, yeah. Yep. So here's my favorite rigid body, this box thing. So you could think of it as we're tracking at some point on the body, but usually center of mass is a good choice. So this is 6 degrees of freedom. And you could write 3 coordinates that specify where the center of mass is, and then you'd say like the 3 Euler angles. If we haven't specified what it is, we just say sort of theta 1, theta 2, theta 3. So we've got 3 translational degrees of freedom and 3 rotational degrees of freedom. And we could use Euler angles. All right. The final one. So here's 2 rigid bodies connected by a ball and socket joint, like your shoulder. So we've got this one rigid body. Let's, just sort of represent it as here's the joint to the other rigid body. This system, how many degrees of freedom is this system? It's going to be at least 6, probably less than 12. Any guesses?
9.
Yeah. Yeah, so for like one of the bodies, you've got, say, 6 degrees of freedom. For the other one, it doesn't have have the 3 translational degrees of freedom anymore, but it does have the 3 rotational ones. So this would be 3 rotational degrees of freedom relative to the first one. So you'd have 9 degrees of freedom for this system. So that means you've got a Q1 to Q9 you'd have to keep track of to describe this. Some terminology here, when we these things we call the Qs, they describe the position and orientation. So if I have, here's my rigid body, here's a rigid body. All right, if I want to describe the position and orientation, those are called configuration variables. So variables that describe position or I guess orientation. They get, in the Lagrangian framework, those get lumped together and called configuration variables. Why? Because they describe the configuration of your system. So when we have constraints on configuration variables, those are what's called holonomic constraints. And so now it's useful because we got 15 minutes left. I will mention the other category of constraints, and this is something where you can't really model some systems most efficiently unless you use Lagrangian mechanics, and that's related to this other category of constraints. So non-holonomic constraints. This is the other main category of constraints. And it's called non-holonomic because you just can't write them in terms of those F functions before. And there's many types. The main one that we're going to care about are constraints on rates of change of the configuration variables. So the most important for us these are constraints on rates of change of generalized coordinates. So they're going to be functions that relate like Q1 dot to Qn dot. And these are sometimes called generalized velocities. There's a lot of abuse of the word generalized. There's going to be generalized forces, and just add the word generalized in terms of the usual mechanics, and then people will think you're talking about Lagrangian mechanics. So this is the most important category for us, and there's a subset of that which is the most important. So usually they are linear in the generalized velocities. And so we'll just write what that form is. This is the main form. Sum from 1 to the number of generalized coordinates. This is a sub Li, so L is now like a subscript. This is these A's are just scalar functions of the Q's times Qi dot equals 0. So this is sort of the main form, and there would be, in this case, L would go from 1 to, we'll write this as S. S is the number of non-holonomic constraints. So let me give you some examples. If I had that something I put up above, but if I have a 2 mass system, but let's suppose that, so this is kind of moving in the plane freely in general, where I've got, here's an angle theta, and I'll call this point where this mass is located as x, y. Okay, so this would be, I haven't added the non-holonomic constraint yet. This looks like it's 3 degrees of freedom. X, y, and theta can all freely vary. But I want you to imagine that under this lower mass, I've put it's like I've put a little wheel, or if you want, I've put a blade, and this will be sliding on ice. So if I've got if I put a wheel underneath, and the wheel will only roll in the direction of the axis of this rod. So I just want you to imagine what would happen if you gave this a push. It's only this bottom mass can only roll in the direction of the orange line. So one way to put that would be if I label this mass down here 1 and this mass up here 2, in general, this mass should be able to move in any old direction. So let's say it should have some velocity that can move in any direction. But we're saying, no, you can't move. The normal component must always be 0. So you could write the constraint as and this is either a rolling, or it's sometimes just called a knife edge, because it's also the same. If this was on ice and I put a skate aligned with that orange direction, then this thing that mass could only instantaneously move in a certain direction. So that constraint can be written as V1, the velocity of particle 1, dotted with n hat equals 0, where n hat is normal to the particle 1 to particle 2 line, meaning it's normal to the rod. In fact, we can even write all of these things out. So this nicely is already in the form of a scalar. It's the dot product of 2 vectors. If I were to write what's the unconstrained velocity, let me give myself some inertial frame here, E1, E2. Then V1 could be written as x dot in the E1 direction plus y dot in the E2 direction. This is the unconstrained velocity. And what about n? Well, n can nicely be written in terms of theta, which is another generalized coordinate here. So what is it? N is negative sine theta E1 plus cosine theta E2. So if I take that dot product, V1 dotted with n equals 0, what will that give me? That will give me negative sine theta times x dot plus cosine theta times y dot equals 0. Let me, with this equation that I boxed up here, I'm going to call this star. This is sort of the usual form for a linear non-holonomic constraint. And you'll notice that this knife edge constraint is in the proper form. So this is in the form of that equation star above. If I said, Q1 is X, Q2 is Y, and Q3 is theta, then this looks like, and then if S equals 1, we just have one non-holonomic constraint, then we've got A11 as a function of X, Y, and theta is equal to, well, no, let's do it in terms of the Q's. A11 as a function of Q1, Q2, Q3 is negative sine Q3. And A1, 2 is equal to cosine Q3, right? Because what is X dot is the same as Q1 dot, and Y dot is the same as Q2 dot. What about A13? A13 is just equal to 0 because theta dot does not show up. Theta dot is Q3 dot, and it's just not present. So this would be it's hard to know how this system is going to move necessarily. You can imagine sort of giving it a shove, and if this front mass can actually move freely, but this mass back here, it has to be moving instantaneously in the direction of the rod. It's going to do some weird stuff. It's not totally weird though. It will move similarly to a shopping cart. A real world rigid body version, which is similar to this, is the shopping cart. You're like, oh my goodness, he's talking about shopping carts. Yeah. So I really like this picture of a shopping cart. And what do I mean? Well, you could approximate the back here when you're pushing your shopping cart through Walmart, right? These wheels are fixed. They don't pivot. These things can freely pivot in the front with a caster wheel. So this thing moves. It has a non-holonomic constraint that's similar to this situation up here. There's interesting dynamics that result. There's something called the shopping cart instability. And you're like, shopping carts seem like the most stable things in the world. Well, that's what you think. So let's end with a video of a shopping cart instability. We already saw a giant safe fall on a Buick. Okay, good. Let's hope this works. I think this shows this is a simulation. I will stop it before it gets too interesting. We've got here in the front, this kind of orange looking thing. That's the blade. So it's as if this thing is moving on ice. The front two, or these blue blocks, are able to freely move. So what's going to happen in this simulation is it's as if we'll be shoving a shopping cart from the front. So you pushing the shopping cart the wrong way, and you'll see, at least in the simulation, what happens. So you give it a shove, and then it actually wants to spin so that it's actually going the right way. So shopping carts will right themselves. They want to move in the direction that they are normally pushed. So I even had some undergrads a few years ago try this out. I probably like the Walmart parking lot or something. So pushing a shopping cart backwards, what happens? What do you know? It turns. It does this shopping cart instability so that it could turn going the right way. So it's real. It really does happen. It's also related to if you're skidding on ice. But we'll just have to talk about that later. So that's it for today.